The following was presented at the 10th Dry Dock Conference. Registration is now open for the 11th Dry Dock Conference. Visit drydockconference.com for more information. The 2025 Dry Dock Conference will take place on the 4th and 5th of June, 2025 in Providence, Rhode Island, USA. This is the 11th International Dry Dock Conference and Advanced Training Forum, hosted by DM Consulting. Registration is now open for in-person and online attendance. Visit our website to register and register early for a discounted rate.
Our next speaker, Sandra Wyman. She's employed by NOAA, but is actually current active duty for the U.S. Navy. She has a master's degree in engineering. She's experienced with dry docking and heavy lift, and she's going to talk about some heavy lift operations that the Navy has completed. Sandra.
All right, thank you, Joe. Good morning, everyone. So as Joe said for that introduction, I am Lieutenant Commander Sandra Wyman, and I'm going to give you a brief overview of the Navy Reserve Soup Salve unit and a few of our recent lifts. So just to kind of cover a summary of this brief, it's an introduction to the NAVSEA Soup Salve unit and our mission, sort of our training path and our primary skill set, a general overview of a heavy lift operation, and then some lessons learned from both the emergent lifts of the USS Fitzgerald and USS McCain, as well as a more recent planned heavy lift of the surface ship support barge. The unit's overall mission is to provide technical depth and deliver operational support capabilities to NAVSEA in the areas of diving, salvage, towing, underwater ship husbandry, heavy lift, dry docking, and admiralty law. In particular, the heavy lift portion of the unit's skill set is a unique reserve-only capability. One of the major reasons for that is we just don't do enough lifts. So by maintaining it as a skill set within the reserves, it allows the Navy to have experts who have done lifts on call, but they don't have to pay us every day of the week. A little bit of the unit history and how we came to be. Prior to the bombing of the USS Cole, there was no heavy lift capability. The USS Cole was the first emergent heavy lift of a large warship, and out of that evolution came a realization of the need to have this capability and the instructions how to do it somewhere within the uniformed service. Over the past 10 years, the unit has conducted or participated in over 25 heavy lift operations, including emergent operations, planned operations, some of which included multiple ships and multiple lifts. Those tended to be smaller vessels, such as MCMs or PCs, that were deliberately being transported over longer distances and through more open ocean conditions than it made sense to have them go independently. Some of our other projects, including tow of decommissioned vessels, support for vessels being transferred for foreign military sale, and a couple of specialized soup salve projects, including the SSSB, which will be covered later in this brief, and the tow of the Bonhomme Richard following her fire. Our general training pipeline involves a qualification as docking observer, typically through a regional maintenance center, occasionally through the naval shipyards. follow-on training in doing additional blocking and stability qualifications. So that's a separate qual on top of the docking observer qual. Completion of the NAVC dry docking course, training on the use of posse, or the commercial version more commonly known as Hexalf, training in setting up vessels for tow and tow operations, and then observation of heavy lift operations. That is the kicker because of the scarcity of heavy lift operations, especially over the past several years. The qualification pipeline takes anywhere from 3 years when there are a lot of operations ongoing and a lot of opportunities, to there are officers that have been in the qualification pipeline for over 10 years. So there are 35 heavy lift billets, but there are actually 42 officers on our roster, and that comes from the nature of the way our billeting works within the reserves and the rotations. It allows people who are being rotated to primarily support other lines of effort to keep working on those quals, again, because of that long timeline and scarcity of training opportunities. So a heavy lift is like a dry docking, except it's in open water, the dock moves, the ship probably has a hole in it, Murphy came to visit, and he probably didn't read the general notes before he got there. The heavy lift team has 3 critical positions. These are the most visible folks, which would be the blocking and stability expert, the heavy lift transport docking observer, and then the heavy lift project officer, typically a senior commander or a captain, who's in charge of the overall evolution. Additionally, there'll be a services coordinator. There's usually somebody representing the load or the command of the vessel that's being moved, the ship repair officer. There'll be members, often there are members of a riding crew, not always. There'll be an independent marine surveyor. The load master from the lift ship will be intimately involved in these operations, and there will be a contracts coordinator. I said that heavy lift starts with a dry docking, but even from the very beginning of writing the contract to execute a heavy lift, it is different than a dry docking. This is seen more as a ship charter and cargo transfer contract, and therefore involves many different clauses that are not typically part of a dry docking. In planning the evolution, the transporting contractor will provide a transport manual, and the heavy lift unit will sort of verify all of the calculations and estimates that were made. So there'll be a detailed review of the transport manual, including descriptions of the heavy lift ship and all her particulars, overview of stowage plans, review of all the block loading calculations and sea fastenings, overview of the loading sequence. The services and logistics tend to seem like something that would be a minor part of this in comparison to all the engineering that goes into planning how to secure the load and safely move her. However, for the most part, ships are not meant to sit empty and without power for long periods of time. And so there is still a need to provide some minimal power, to provide firefighting capability. In particular, with the lift of the McCain and the Fitzgerald, what was very quickly realized is that international fittings often aren't, and that the lift ships, none of which are designed for lifting a destroyer as their primary customer, you know, their primary service are oil platforms or a series of barges, were not equipped natively from ship systems to provide the amount of firefighting water and power needed to support the destroyers. Planning the lift, there are usually very tight considerations for weather and tide. And unlike a docking in a floating dry dock, which generally takes place in more protected and sheltered waters, we need to find an area that is deep enough to support the lift vessel submerging to pick up our load. Most lift vessels are not designed to have bottom contact. So as a result, we're generally pretty far offshore in comparison to where you would locate a floating dry dock. And throughout the evolution, we're subject to sea state and wind. A few times, the only reasonable place to conduct the lift was rather close to the main channel. And in one instance, it was right in the main channel. So there's a lot of coordination that has to take place in the background with port control in planning to basically shut down a channel for the majority of a day. In looking at the loading calculations, the proposed route, and the risk of weather, the typical sea states along that route are taking into consideration. There's a lot more sea fastening and a lot more work that goes into planning a lift that's, say, going down the coast during hurricane season or going across the Pacific than something that's going from Norfolk down to Charleston. And I already mentioned some of the contracting considerations. That wasn't supposed to show up that way. All right. So in a dry dock, as all of you know, you have your keel blocks support the displacement of the ship, and you have side blocks to resist the overturning moment and support a small fraction of the ship's displacement. In the heavy lift, we add spur shores to further resist the overturning moment that comes from rolling at high angles and the additional wind loads that the ship will face in transit. And you have sea fastening to resist the longitudinal and lateral motions or sliding of the load on her blocks. There are two ways of approaching these calculations. We're going to review the calculations as they're outlined in the U.S. Navy tow manual, which is a little bit different than the method that's presented in Principles of Naval Architecture. The Navy tends to look at these calculations as dynamic loading or acceleration factors that are unitless factors of G and then are multiplied by the displacement of the vessel to get a total load. For the most part, this yields the same results. But in starting the planning of an evolution, the first thing we're looking at is the block loading across the typical docking plan. Most of our assets that are heavy lifted are in a damaged condition. So where the trapezoidal method of calculating block loads works well if you have a continuous keel line, as you can see in this example from the McCain, which had a significant area of underwater damage, that would not have been adequate for transporting her over open water, and using the moment area method produced much more accurate results, which were later verified with strain gauges. The load is always the frame of reference in planning the lift evolution. And so we're looking at rotation and translation across 3 axes. Everything in planning the load movement is measured relative to the center of gravity of the lifting ship. This is something that is a little bit different from the way most other calculations are presented. A brief overview. So here is the vertical acceleration formula. One note to call your attention is that first one accounts for the vertical displacement of the ship initially, and then everything that follows is accounting for the dynamic sea loading. So the pitch and roll of the load in transport and the period of pitch and roll are critical in determining the amount of sea fastening. There are tables provided in the tow manual to help one make a first best guess in pre-planning a lift. But typically, that's all that is a first best guess. And then the sea fastening design is further refined based on the seakeeping characteristics of the lifting vessel and data typically gathered from NOAA's buoys or other oceanographic sources about the expected sea states and wave periods on the route of transit. That's why the route planning is a large part of looking at one of these evolutions. Similarly, the athwart ship's acceleration is shown here, again looking at max angles of roll and pitch, periods of roll and pitch, and distance of the CG from the CG of the lift ship. And you can see in the lower photo, you have a side block, and then you have some sea fastening preventing motion of that side block across the deck of the lift ship. One of the first considerations in planning sea fastening versus looking at a dry dock is I'm not trying to do maintenance on this vessel. I'm just trying to move it from point A to point B safely. So whereas in planning and dry docking, I may want very high blocks to facilitate dropping a rudder, accommodating a propeller, pulling shafts, doing a full inspection of the bottom, whatever. In this case, I want the smallest blocks I possibly can get to keep the CG of my load as close to the CG of my lift vessel as I can. And here you can see 2 MCMs nested side by side on a lift ship, along with the formulas for longitudinal acceleration. The step-by-step of how to calculate sea fastening is presented in the tow manual. It would be longer and more involved than Joe wanted me to get into in this particular forum. But, and I think they do a reasonably good explanation of how you get there. In contrast, Principles of Naval Architecture takes a look at the forces independently and then adds them to the total displacement. So here are some examples of sea fastening on recent lifts. You can see both the McCain and the Fitzgerald passing each other in Yokosuka. One thing to note is the shoring on the McCain and that gap in the shoring in order to accommodate her below the waterline damage. Another thing to note, although it is somewhat less obvious in these photos, is that the McCain was loaded crossways across the lift ship, whereas the ship that lifted the Fitzgerald was large enough to accommodate loading her straight on. Unfortunately, the Navy does not maintain any of its own lift ships. Again, we just don't do this often enough to justify the cost. So we are tied to what is available in commercial industry to accomplish the work at the time of need. Due to some downturns in the oil industry, there are fewer lift ships available than there were even 10 years ago. And so the close occurrence in time of both of these lifts really had our lift contractor overloaded, both in the engineering department and in the vessel availability department. A typical planned lift is anywhere from 60 to 45 days to plan the evolution. These lifts were both accomplished within 45 days of each other. This also stressed the reserve unit quite heavily because the majority of reservists actually have other jobs, but as a portion of our service, for an event like this, most of us had less than 3 or 4 days notice to take off and go to Japan and assist with this evolution. Unfortunately, due to the way we are set up, some of that resulted in a little bit of a rotating pool of people coming through. And that was one of the large takeaways, was that there was frustration on the part of the crews of the lifted ships when the face of the person they were dealing with changed on a roughly every 2 to 3 week basis. One of the other things you can see in the photos, you have 2 officers inspecting some of the shoring that gives you a good sense of scale for the spur shores and the sea fastening being installed on Fitzgerald. And here's a little bit better overview of the positioning, particularly of the one of the ships across the deck. Here's what that looked like in real life. The guideposts are exactly that. They are positioning markers. So when the lift ship submerges, there are very few landmarks, if you will, to use to properly center and position the load over the build. So that is what the function of these guidepost bumpers. They also provide some sea fastening support, but because they will be fitted up tightly against the hull during the final preparations, but they're not included in most of the planning as anything other than positioning guides. This is an example of an MCM guidepost layout with two MCMs side by side on the lift ship. One of the challenges in moving MCMs is they have a tumble home hull. So whereas many ships, the max beam would be at the main deck, the MCMs actually turn slightly inward. So they get slightly narrower as you come up to the main deck. And this was, when this lift was actually conducted, this was not fully accounted for in the planning of how those guideposts would contact the hull to verify that the MCMs were firmly over their build. So the final configuration actually had them somewhat more askew. This is a brief overview of POSSE, or again, the commercial version of Hexalv, showing that we can model the lift. This is often used as a secondary means of verifying the loading plan and modeling whether or not the lift ship is adequate to carry the load fully and fully support it. So the two big, sort of infamous emergent heavy lifts the unit recently participated in were the response to the collision of the USS Fitzgerald in June of 2017, just southwest of Tokyo. The ship was towed to Yokosuka for temporary repairs and then heavy lifted to Pascagoula for further repair. Unfortunately, about 2 months later, the McCain had her collision in August off the coast of Singapore. She was initially towed to Singapore for temporary repairs and then lifted to Yokosuka for permanent repairs. There had been a plan to lift her to Yokosuka to perform some initial remediation and then do a second lift either to Pascagoula or to Bath. So some of the lessons learned that came from planning the 56, one of them was there was a tight time frame and a very small weather windows for some of the work that was conducted. And so after the ship was positioned over the build, but before she was fully deballasted, the work crews started positioning the sea fastenings. This created some future problems, because the ship, the lifting ship, was flexible relative to the amount of load that she was carrying into her positioning. And so those sea fastenings that seemed to be tight up against the hull and firmly supporting the load when they were inspected, once the ship was fully deballasted and in a seaway, there was gapping in them. And that led to the cracking that you can see in the picture there. Now, in a typical dry docking, cracking like that for whatever reason, or the hull deflection shown lower down that was also a result of motions in the shipway, would be considered a major incident. I'd like to remind you that this particular ship already had a 65-foot hole in her side. So relative to the rest of the issues with the ship, this was minor, but it was a lesson learned for the unit in planning the lift to make sure that none of the sea fastenings are installed until the lifting ship is fully deballasted and in a stable configuration. The other cause of the damage, which was later proven by finite analysis modeling done from a team of reservists and engineers at Carderock, was that the relative motion between the load, which was loaded crosswise to the lifting ship, and the lifting ship, even after the sea fastening was rebuilt in a tighter configuration, there was still a difference in the amount of flexibility and give in the seaway between the two ships and excess motion that caused some damage. Also, the standard docking plan is looking at supporting a ship in a dry dock that we assume doesn't move. And so the blocks are not always on the intersections of frames. One of the lessons learned out of this was to take the docking plan and very carefully look at where the blocks are placed in relationship to the ship's internal structure. The suggestion and the annotations in an upcoming revision of the tow manual are to use the docking plan for onload and then fit up additional blocks once the cargo is loaded and lifted as part of the sea fastening process. The other revision to the procedure that came out of this was that when installing sea fastening, not only to make sure that the lifting ship is fully deballasted, but actually to sally ship by 1 degree in each direction. So induce a deliberate list of 1 degree, install the shores tight against the hull of the load on the opposite side, so on the high side, and then roll her in the other direction by 1 degree, and install the sea fastening tightly against the other side. For the most part, when we did this on the next lift, it worked well. Unfortunately, there was a new problem. So the team did start with the original docking plan and then moved the blocks to accommodate the intersections of the frames, and they sallied ship when they loaded her on. This ship, while it had room to fully support Fitzgerald in a fore and aft configuration and mitigate a lot of that motion between the load and the lifting ship, the deck was not initially strong enough to support Fitzgerald's full load. And so rows of grillage were installed to better spread the load of the DDG across the cargo ship. The positioning of the grillage and the revised docking plan was designed based on tables of offsets that were provided with the hull. But the team during the design used the longitudinal framing tables rather than the transverse framing tables, which didn't fully account for the change of rate of curvature of the hull. And as you can see in the picture there, the grillage went through the Fitzgerald's hull in a total of 2 places into a fuel tank. Again, in a typical docking, this is something that would be considered a major incident. And while it certainly delayed the evolution and was additional damage to the ship, the state of the Fitzgerald that necessitated heavy lifting in the first place, this was minor damage in comparison. A more recent and planned evolution was the transport of the surface ship support barge. So the surface ship support barge was a Liberty tanker ship from the World War II era, the ones that were somewhat infamous for breaking apart while at sea. We took her midsection, added approximately 10 feet of new extension on the forward and aft ends, and then used her to support nuclear work on aircraft carriers for many, many years. This evolution involved undocking the ship at Newport News shipyard, transfer up the river by wet tow to Killanis, docking at Killanis, and then transferring via SPMTs onto a seagoing barge for eventual offloading at Alabama shipyards. And by the nodding heads, I see a few familiar faces that a good handful of you were also involved in this evolution. So there were many moving pieces. From the heavy lift unit perspective, no one in the heavy lift unit at that time had familiarity with the SPMTs and the rolling transport of vessels. So the folks at Burrard Transport were very patient with us as we asked them many, many questions and reviewed their calculations. One of the most interesting coordination points was maintaining consistent draft between the floating dry dock at Killanis and the barge as the weight of the SSSB shifted from one floating structure to the other. A few of the lessons learned and complications out of that evolution was the SUPSALV or NAVC OSC requirements were not written into any of the contracts among all the parties involved in this evolution. That was an oversight on the part of the contract writers, where the heavy lift unit was responsible for overseeing the safe transport of this vessel and was very cognizant of the potential public affairs disaster should things go wrong. But our oversight and our requirements for whether it was for sea fastening, whether it was for observing either the undocking evolution at Newport News or the docking evolution at Calanus, our requests for calculations, and our requirements for secure of any internal loads to the SSSB that could come loose were not part of the contract planning process. And that was one of the big feedback points throughout NAVC was to include heavy lift and the heavy lift oversight requirements a little bit earlier in that planning process. One of the points of contention at the time of planning this lift was a large work platform that was located inside the SSSB, affectionately called by the team the 21-ton radioactive Frisbee. The language in the contracts in question referenced good shipyard practice to secure said 21-ton radioactive Frisbee. For the wet tow, that was more than adequate. For sitting in a dry dock or pier side in common controlled waters, the standard good shipyard practice of these straps that were used, again, would have been more than adequate. But when applying the calculations for the sea states, that we determined the tow was likely to encounter between Calanus and Alabama Shipyard, along with a safety of margin, it was far from adequate and actually was undersized by a factor of 4. Thankfully, Barrage Transport eventually agreed with our determination, and the 21-ton radioactive Frisbee was properly secured. But it was just one example of the position the team found themselves in of having the oversight responsibility, but no true authority over the evolution other than the goodwill of some of the contractors involved. Another interesting aspect of this evolution was, as I mentioned earlier, the SSSB was a section of a Liberty tanker, rather notorious for breaking apart at sea and for the brittle nature of their steel due to its high manganese content. Actually visible inside the SSSB when you tried to walk around were large crack arrestor plates that were then marked with yellow and black tape as a trip hazard. I tripped over them at least once while carrying something. The sea fastening calculations and the guidance in the tow manual don't direct either the transporting company or the heavy lift team to look at the structural strength of the load. The assumption is that that is not the issue. The issue is just securing it onto the transporting vessel. In this case, we did in fact take a look at the structural strength of the load, including digging up old drawings from when the extensions had been added, believe it or not, pulling drawings from the Library of Congress that showed some of the original structure on T2 tankers, and taking some UT gauges and making our own measurements of the thickness of the steel in place. And as it turned out, the flat faces of the SSSB, which you can see one here in the lower photo, which both made the wet tow very, very slow, were the point of weakness. And we actually had to require the transporting contractor to double the amount of shoring that they had anticipated using, because the slide force of the load going against the shoring would have buckled or more likely cracked that plate. So the revisions to the tow manual will now include notes to review the structure of the lifted load prior to signing off on the sea fastening plan. Most of the time, the sea fastening just following the basic guidance in the tow manual is more than adequate relative to the ship's structure. This was an unusual situation in many ways. And I have finished up just a few minutes early, leaving time for questions. Somebody has to have a question, or Joe's going to leave me standing up here forever. Go ahead.
So you said that lead time for design was 60 days, 45 days. Did that include all your calculations and the checks and rechecks?
Yes. So ideally, we would have between 60 and 45 days. In both the McCain and Fitzgerald timeframe, we had much less time than that. And due to some staffing shortages at Schmidt, rather than Schmidt completely preparing the C-fastening design and then turning it over to Heavylift as a set of second checkers, we were designing a set of C-fastenings right along with them and then passing the design back and forth.
So if C-lift companies have limited supply or overloaded with work, is there a delay between your design and actually their execution of the?
There can be. There were actually two different contracting methods that were used in securing the work for this. SoupSolve maintains standing salvage contracts with multiple companies. And you'll forgive me because I do not remember which lift was contracted which way. But one of them was done through the salvage contract, which was an existing contracting vehicle. And then the salvage company was basically directed, go do this. And so they subcontracted Heavylift for that. The other one was done more directly as an independent contract. And that also caused some differences in how they were managed and how the oversight was managed. There was another question somewhere.
Hi. Could you tell us how did you get the roll periods and the pitch periods for the ship with the load?
So there is a table in Chapter 8 of the tow manual that gives you notional roll and pitch periods based on the length of the vessel in question. As part of the package of data provided by the lift company, we also ask for the sea-keeping characteristics, but the models do not account for the loaded condition as well as they account for the natural unloaded condition of the lift ship. So there is some potential error in there. There was somebody else over here.
Yes, with a short time frame that you operate under, how do you have time to build a posse model of the heavy lift ship?
We don't always. Ideally, we'll have one person that we task with building that model. We also work with, we have support from OOC's main naval architect, who uses that software much more frequently than any of us in the reserve unit do. Sometimes we'll get it from the lifting contractor. How detailed and accurate that model is will vary somewhat on how much time it is. It is not our primary means of verifying the C-fastening. It's more yet another check that we haven't missed anything glaring.
So my question is regarding the lift itself. Do you take into consideration the KM of the lift ship? And do you have like an overall GM that you basically calculate to evaluate the stability of the, the ship overall?
Yes. So both data points are part of the transport manual, where we're looking at both the total stability of the combined loads, stability throughout between 3 and 5 points during the loading process. And then one of the major concerns is windage. and wind loading when the cargo is fully positioned on the lift ship.
Yeah, does the government have any restrictions on the companies that you hire to do these lifts? And if not, who do you primarily use?
So I am not aware of any restrictions, and that actually came up several times doing both the McCain and the Fitzgerald lifts, because the company that did the calculations was Dutch. The one crew on one of the lift ships was primarily Russian. The other crew was heavily Indonesian. And so part of running the Evolution was there were always US naval personnel on and about the loads as they were being handled.
So they haven't given you any restrictions on, you'd go strictly by availability in the location that you're lifting the asset?
There might be some restrictions that I am unaware of, but in the case of these two Evolutions, it was very much a question of who was available. I mean, ideally, if we had our choice of the perfect ship, we never would have loaded McCain crosswise. We sort of suspected that that would potentially cause issues, but it had never been done one way or the other, and there wasn't another vessel available. And that is one of the challenges facing heavy lift as a result of changes within the oil industry. There is a table in the tow manual that is very out of date with a summary of available lift ships worldwide. It gives you a good idea of capacities and the types of ships, but many of those ships have been either scrapped entirely or converted for other uses. Anyone else?
The loading cracking issue that you mentioned. Could you go over that again? Yeah, it's a little confusing.
Sure. Let me see if I can go back to get you a picture. So, and Joe, I do have a separate presentation on this, but I was not the person who did the finite element analysis proving exactly how the cracking happened. But in short, was a result of the motions between the McCain and her lifting ship. So as the lifting ship went through the seaway and is responding to the seaway, the load was also responding, but at a different frequency. And the load was much stiffer. So they weren't moving in tandem with each other. And as a result, the sea fastening was making contact with the hull off and on, and it was basically fatigue.
And then they didn't deballast, they did not deballast right away? It's a little...
So that, where you see the water streaming out, that is on a fuel tank, on a compensated fuel tank. So there was a mixture of seawater with fuel floating on top in the tanks. And the way a DDG is designed to maximize stability of the load, we did not fully deballast her. Once the cracks were noticed, the lift ship took a pause in Subic Bay, and the blocking was adjusted. There was additional shoring added. There was a patch put on the cracks. So she didn't just continue in that configuration.
So are you modeling these movements before actually make the movement?
We did, after the fact, do an analysis in modeling, which I was not part of, to determine why this happened. It was honestly, at the time, an unanticipated result. Anyone else? One more.
Can you just go to the next slide there? So, I think you said that as you were sallying to load up, I guess your cappers. Was there any intent to dive the block set in advance, like to spot that sort of thing, or no intent to dive?
To be honest with you, I was not there for this evolution. So I can't tell you exactly whether or not there were divers as they were loading or what the divers were looking for. It's part of our procedures that there always should be divers swimming the blocks. There was some question of whether or not the grillage would contact the hull, and it was basically one engineer arguing with the other engineer, and based on the tables, they believed that it wouldn't. So I'm not sure if the divers could have caught that, or I think the divers are primarily focused on contact with the wood.
In the event that it was determined that the grillage would contact the hull, would you still have gone through with the evolution?
Oh, that's an interesting question. The damage the grillage caused relative to the damage that was already present on the ship was minor, but the grillage did contact a fuel tank, and that needed to be contained and at least partially repaired for transit. And in the end, they ended up having to cut and adjust the grillage anyway. As a potential HLPO, I would have waited and modified the design, just because in the end, they lost more time in that evolution than it would have taken to modify that grillage in the first place.
Unlike a typical dry docking where most of the keel blocks and side blocks have a spring constant or a block coefficient of about the same number. In this situation where the spring constant's modeled into your model, where typical blocks are constructed out of timber and concrete and the shores were not.
Yes, so I skipped over a lot of the first steps of planning a lift. So the ship is sitting on its typical dry docking cradle with keel line and side blocks for the most part with wooden caps. And then the sea fastening is added after. I just didn't want to bore the audience with all the steps of planning the docking. So in planning the spur shores, which are what would have direct contact with the hull, the spring constant is accounted for. One of the upcoming revisions of the tow manual covers is the original tow manual assumes wooden spur shores, which of course is not correct anymore, but was what was used in time that the document was written. So in doing our calculations, and obviously in the planning the transport company did, we were looking at steel.
For the top middle picture, that was the Fitzgerald, correct?
Yes.
So,
it's either the yes, it's the Fitzgerald.
So I guess maybe just an underwater appendage question, because it looks like it's sitting pretty low. Was there any type of special consideration for the props or the sonar dome? I'm assuming it's kind of overhung, or?
So the sonar dome is overhung in this case. There are several ways of dealing with the props, from cutting a hole in the deck to what we actually did was remove 2 prop blades.
Perfect. Thank you.
All right, thank you, everyone. I will retreat.
For more information on this topic and others like it, please see our technical papers. Visit drydoctraining.com/technical-papers or contact DM Consulting at drydoctraining.com/contact-us. Registration is now open for the 11th Dry Dock Conference. Visit drydockconference.com. Thank you for watching.